Davisson and Germer experiment. C.J. Davisson and L.H. Germer in 1927 and G.P. Thomson in 1928 observed diffraction effects with beams of electrons scattered by crystals. Their experiments played a major role in verifying the de Broglie hypothesis and demonstrated the wave-particle duality. Now, wave-particle duality was put on a firm experimental footing. It represented a major step forward in the development of quantum mechanics. Davisson and Thomson shared the Nobel Prize in 1937 for their experimental discovery of diffraction of electrons by crystals. The experimental arrangement used by Davisson and Germer is schematically shown. It consists of an electron gun consisting of a heated tungsten filament F that released thermally excited electrons, which were then accelerated through a potential difference, giving them a certain amount of kinetic energy. They are made to pass through a cylinder with fine holes along its axis, producing a fine collimated beam. The experiment was conducted in a vacuum chamber. The beam is made to fall on the surface of a nickel crystal. To measure the number of electrons that were scattered at different angles by the atoms of the crystal, an electron detector that could be moved on an arc path about the crystal was used. Detector was connected to a sensitive galvanometer. By moving the detector on the circular scale at different positions, the intensity of the scattered electron beam was measured for different values of angle of scattering theta, which is the angle between the incident and the scattered electron beams. The electrons that bounced off different layers had interfered with each other, just like waves. They generated a diffraction pattern with unexpected peaks. The experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity I of the scattered electron for an accelerating voltage of 54 volt at a scattering angle theta is equal to 50 degree. The de Broglie wavelength lambda associated with electrons using equation lambda is equal to 1.227 upon under root V nm, we get lambda is equal to 1.227 upon under root 54 nm is equal to 0.167 nm. There is an excellent agreement between the theoretical value and the experimentally obtained value of de Broglie wavelength. Davisson-Germer experiment thus fully confirmed the wave nature of electrons and the de Broglie relation. Use of the wave properties of electrons is made in the design of electron microscope. An electron microscope uses beams of electrons instead of rays of light to take us down to nano dimensions. By using world's most powerful microscopes, you'd be able to see things 100 million times smaller. Bacteria, viruses, molecules.